Hello and welcome to the channel. I am Pratik and today we'll look at cruise control of a vehicle where we'll see how a PID controller can be used in a closed loop environment in order to maintain the speed of a vehicle constant. Before going into the simulation part, we'll look at what cruise control actually does. So when a driver is driving on a highway and he sees a long stretch of road ahead of him or her without any significant disturbances on the road, so in that case the driver would want to maintain the speed of the vehicle somewhere around his desired speed, and that would more or less be constant along the entire way. It would be a tedious task for the driver to manually maintain the speed because the vehicle would be running approximately at a constant speed. So in our case we have assumed that let's say the driver wants to maintain the vehicle at a speed of 75 km per hour. So the cruise control system gives the vehicle the freedom to lift his foot from the accelerator pedal, and still the vehicle would continue at that desired constant speed. When the driver sees that there is a highway and he wants to maintain the speed of the car constant, then the driver would simply bring the vehicle to that particular speed, which is 75 km per hour here, and then lift his or her foot from the accelerator pedal. After that, the driver activates the cruise control system and the vehicle would maintain its speed at the set point, which is 75 km per hour here. This is essentially how the cruise control of a car works. Now we will look into some mathematical modeling of this cruise control system so that we arrive at mathematical equations which we can use to build our simulation later. So to arrive at equilibrium equations of the vehicle, we'll first look into the free body diagram just to know what all forces are acting on it and what equations can be drawn out of it. So this is our car. The car will have a mass m. Because of gravity, a force of mg will act downwards. Since the road is rigid, it will provide an equal and opposite force, normal force n in upward direction. The engine will produce a force Fe. We have taken Fe as the engine force here. There is a force produced by the engine due to combustion. Fd is the aerodynamic drag. Fd is the aerodynamic drag which is experienced by the vehicle as the vehicle moves forward and wind hits the vehicle in opposite direction. There would be some drag due to it, and that would act in the opposite direction of engine force. That is, Fd would oppose Fe. So this is the free body diagram. Now we know that the vehicle is moving forward, so the resultant force would ultimately be in forward direction, and therefore the vehicle would accelerate in the forward direction, that is along the direction of Fe, and this acceleration we are denoting by A. Now we have some assumptions here. First of all, we are assuming that a vehicle is moving on a flat road which has zero slope. Slope here itself is not taken into modeling, but in the simulation we will see that we have taken the slope as a disturbance later. The next assumption is that aerodynamic drag force which we have taken, we have assumed that it is directly proportional to V. However, this assumption is only true for very small objects. It is defined by Stokes' law. However, when we consider large objects, Fd is actually directly proportional to V square. But in this case we have taken Fd proportional to V just to simplify the scenario, because if we take Fd proportional to V square, we won't have a linear differential equation, and that would complicate the calculations. So for simplicity of the situation, we are considering aerodynamic drag force as being directly proportional to V as defined by Stokes' law for small objects. Now we'll look at the mathematical modeling where we'll try to derive some equations of motion out of this free body diagram. First of all, we know that the normal force and the mg cancels out each other. Since we know that a vehicle is effectively moving forward, therefore the resultant force will be acting in forward direction, and that is why Fe minus Fd will be equal to mass times acceleration of the vehicle. Here Fe, which is produced by the engine, will be directly proportional to the throttle position of the engine. So throttle is something which allows the air to flow into the engine, and based on that the amount of fuel injected into the combustion chamber is decided. As a result, if we increase the throttle, the power or ultimately the force which is produced by the engine increases, and therefore Fe is directly proportional to the throttle position. This throttle position in our case will be directly proportional to the input, and here the input is actually the error signal which is generated when we compare the desired set point speed and the actual speed of the vehicle. We'll see this later in the simulation. So we know that Fe is proportional to input, and that is why we are attaching a constant here. So Fe equal to K1 times the input which is given to the throttle. The aerodynamic drag force, as we discussed previously, we have assumed it is proportional to the velocity of the vehicle v, and therefore Fd equal to K2 times v, where K2 is a constant. Now replacing all these in the second equation, we see that K1 times the input minus K2 times the velocity of the vehicle equal to ma. Now we know that acceleration is dv by dt, and therefore m dv by dt is equal to minus K2 times the velocity of speed plus K1 times the input to the throttle. Rearranging this, we get our final differential equation, which is dv by dt equal to minus K2 by m times v plus K1 by m times the input to the throttle. This is the final differential equation which we'll be using to build our simulation. So let's jump to the simulation part. So next we will look at how to model this particular differential equation as well as the entire cruise control system in a closed loop feedback scenario. Looking at this differential equation, we know that it is a first order differential equation, and therefore we would definitely need an integrator here. Along with this, we will need a sum block. So we have the sum block here. We would need another sum block in order to simulate the disturbance. So here the disturbance is actually simulating the slope. When a vehicle encounters a slope, its speed would get disturbed. Either it would increase or decrease depending on which type of slope it is. If it is an upward slope, the velocity or speed will tend to decrease. However, if it is a downward slope, the velocity or speed tends to increase. So here we would simulate that slope using the change in velocity. So this output is v. Here we are only concerned about a straight line motion. Therefore for our case we can say that velocity and speed are same, so I'm using the term interchangeably. So we are getting v here, so this must be dv by dt, and from here from this differential equation we have dv by dt is equal to K1 by m times the input minus K2 by m times the speed v. So this signal is coming here with a gain of K2 by m, so we need a gain block. This will have a gain of K2 by m. K2 in our case is 100, m is 1000. So these are the so mass we have taken as 1000. We have assumed that the mass of the vehicle is 1000 in our case. The value of K1 and K2, which are taken as 2 and 100 respectively, are obtained by hit and trial. These are not empirical values. So these are the values for which it was found that the system works perfectly. Here the gain for this particular block will be K2 by m, which is 100 by 1000. we'll connect this here, and this will be connected to this final output. So here we'll get the final velocity of the vehicle. Because this particular speed will have some disturbances which will be input from here, and then we'll get the final velocity or speed of the vehicle. So we need a scope for observing that speed. So we'll connect the scope here, and this output is the final speed of the vehicle. We'll call this V final. So we'll take this V final, we'll connect this here. So V final multiplied by K2 by M, and this has a negative sign, so we'll change the sign here to minus. So this part is complete. Next we have K1 by M times the input. This input is typically the input which is provided by the PID controller. It is the PID controller's output. So we'll need a PID block. Now the output of this PID block is the input that is written here, and this should be multiplied by K1 by M. So we need another gain block here, and the gain value will be K1 by M, which is 2 by 1000. Connect this. So this particular signal is K1 by M times the input. We'll have to tune this PID controller once the modeling is complete. We'll look into that in a while. So we'll worry about this disturbance later. First, we need to make it closed loop. Essentially, this is what is the plant system or the vehicle which we are trying to design. This was the equation which we have modeled here, and then we need to close the loop so that it becomes a closed loop system. For that, we'll need another sum block with a negative feedback. So this signal will come from here, V final, which will be compared with P reference, and then it will give an error to the PID. This is actually the error. This is error in speed. As a set speed, we need a constant block. This will serve as the speed which is set by the driver. Let us assume that the driver is trying to fix the speed at 75 km/h, which we saw during the introduction to this cruise control. So we have the error signal here that is given to PID, which is amplified by this gain, not necessarily amplified, and then it is given as input to this plant. This plant will have this disturbance here. So I'll model this disturbance using a signal builder. We could have also used unit step, but the signal builder gives us more flexibility in terms of what type of signal we want as a disturbance here. We'll connect this here and then change it to minus. So in this signal builder, we'll try to model the disturbance signal. Here, first of all, we know the simulation time we have set as 300 seconds, and so the time range for this should also be set as 300. Suppose we want the disturbance to start at around, let's say, 125 seconds, and the amplitude of the signal, let's say our set speed is 75, so we'll want this disturbance to have a magnitude of around, let's say, 30 km per hour. This amplitude should be 30, and then I would want this disturbance to gradually build up instead of having a instantaneous rise. So if you observe this because of this negative sign, this increase in V is actually reducing the final speed of the vehicle. So this is kind of simulating an upward slope, because as the when at 125 seconds, when this value of V starts increasing, the final value of V starts decreasing, which means the vehicle is moving in an upward slope. And also this V continuously increases. Let's say we make this time up to 250 seconds, so this V is increasing right from 125 to 250 seconds. So it means that the slope on which the vehicle is moving, the upward slope, that slope is also increasing. And then at 250 seconds, let's say we want our slope to remain constant. So here still there is a slope, because this V has a particular fixed limit of 30, and then the only thing is that this 30 remains constant after 250 seconds. So slope is still there, but that slope is becoming constant after 250 seconds. So this V final will react accordingly, and we would expect the PID to manipulate the output signal, the signal which is going as input to this plant. It should manipulate that signal in such a way that the final speed at which the vehicle is running is more or less in close vicinity of this set speed. Now, since our modeling here is complete, the loop is closed, we would want to tune our PID. So for tuning that, we have multiple methods. One would be to use hit and trial and try with different values of P, I and D, see what response is closer to what we actually expect. Or MATLAB provides this automated tuning, where if you click this, it will try to tune this automatically. So we'll try this. As we can see, it is compiling the model. So this is our PID tuner dialog box, where it has itself tried to tune the PID controller, and here we can see the controller parameters which it has set. And if we want, we can write these parameters back to our PID block. Or if we want to tune, let's suppose we want faster response time or slower response time, and depending on what kind of transient behavior we want, we can move this slider, and then it will adjust the PID values accordingly. Once we are satisfied with the PID values, we can do this update block, so that it will write the tuned PID controller parameters back to the PID controller block. So we'll click on this. Once it has written the PID values back to the block, we can close this dialog. Okay, so our PID values have been written back to this block. Now our modeling is complete. We would also want to see the disturbance signal on the scope, so we'll connect that also here. So this is our disturbance signal. Now we have set the simulation time as 300. Let's run this simulation and observe the effect of this disturbance on the set speed, and how the set speed is being maintained by the controller, and what is its effect on the plant. Okay, our simulation is complete, and we can see the value or curve of final speed and a disturbance signal in the scope. So this is the curve that we have obtained. Here the initial speed we have taken as 0. We can also change this to some other values. Suppose we want our initial speed to be 30, and from the 30 km per hour itself we want the cruise control to take control of the accelerator pedal, and then make the set speed as 70. We'll set this initial value to 30 and then run the simulation again. So the simulation is complete. We can see the curve in scope. This is our final curve. Here we can see we started from 30, then the controller tried to reach the set value of 75 as soon as possible. We can see here in less than 25 seconds it tried to reach the value of 75, and therefore the input provided to the throttle would have been very high. That is why there is a slight overshoot here. The speed goes above 75. This is not desired in an ideal cruise control system, because this could come as a safety issue, because in any case the speed should not go beyond what the driver has set. In a simulation this is quite feasible, and here we can see that at 125 seconds, as the disturbance signal begins to rise, the value of V disturbance begins to rise from 0. There is a slight dip in velocity or speed, because we took the case of a simulation of an upward slope, so this increase in V causes a slight dip, but then the PID controller takes charge, and then the speed is again restored to 75 km per hour. Again, when the disturbance signal becomes constant at 30 km per hour after 250 seconds, here the disturbance was continuously increasing, so the PID controller would have been increasing the value of input to the throttle, but then when it suddenly becomes constant, there is a slight increase here also, but then again it comes under control after few seconds. This is how PID controller along with the model of the plant can be used to simulate a cruise control, and this is exactly what happens in a cruise control system in a car, where the driver sets a particular speed which was 75 km per hour here, and the plant as well as controller strives forward to achieve that or to maintain that particular speed, even in case of disturbances or perturbance in between. This is what I wanted to explain using this simulation. I hope this helped. If you liked the video, please hit the thumbs up button, and please subscribe to the channel for more such interesting content. Thank you.